Christian Karchansky. Welcome to another problem from a real exercise book from the University of Mumbai from 2019. We are finding the limit. Now we will solve example number 2. This is not an easy example, the one with the factorial and the denominator n to the n. The method that should be used here is the Squeeze Theorem, and I will show you the appropriate bounds to apply here. These will not be typical, standard bounds. I'm not explaining the basics of the Squeeze Theorem, because I've already covered that in a separate course on the subject, which I warmly invite you to check out. Here, I'm focusing solely on this second example. Here it is, and as we said, we are going to aim for the Squeeze Theorem, Sandwich Theorem. But before we get to those bounds, let's get a feel for what this sequence is all about. N factorial in the numerator, n to the nth power in the denominator. The first term of this sequence will be 1 factorial divided by 1 to the first power, so 1 factorial is 1, so 1 over 1, which is 1. What will the second term of this sequence look like? 2 factorial on top, 2 to the second power on the bottom, so 2 factorial is 2, 2 to the second is 4, so 2 over 4, which is a half. The third term of this sequence, 3 factorial divided by 3 to the third, so 6 divided by 27, which is 2/9. The fourth term of this sequence, 4 factorial divided by 4 to the fourth, write it out somewhere on the side, and when you simplify the fractions, you'll get 3/32. Continuing as if we were calculating, 5 factorial divided by 5 to the fifth power, after simplification, we'd get such a fraction, and so on. And we know roughly how this sequence is formed. Generally, any term of it can be expressed by such a formula, right? In the numerator, we have a factorial, and in the denominator, n multiplied by itself n times, because n to the nth power is indeed that much. Take a look at the numbers that result from this sequence. First, it's 1, then a half, then a smaller 2/9, then much smaller 3/32, then very, very smaller 24 by 625. If you felt like it, you could even write out the first 10 terms, why not? And you would notice that these fractions are decreasing. They are getting smaller and smaller, smaller and smaller, smaller and smaller. Intuitively, we sense that this sequence tends to 0, that it converges to 0. If we were to take 100 factorial here, although calculating 100 factorial would obviously be very difficult, 100 factorial over 100 to the power of 100 would already be a very, very small number. A very tiny fraction. So, our starting point will be that we assume that it converges to 0. But of course, we are in mathematics, and our intuitions, guessing, assuming, are not arguments at all. We will have to show that it actually tends to 0. But we have some starting point for the Squeeze Theorem, right? We expect we will go in that direction to show that the limit is equal to 0. How did we do it in the Squeeze Theorem? Here, we are guessing that this converges to 0, right? But we don't know that, which is why I put a question mark above this arrow, because we don't know it yet, we can't say that we know it. This is our, I don't know what to call it, guess, hypothesis. No, hypothesis is too strong a word. Guess. In the Squeeze Theorem, you would take this sequence without the limit, because we are not bounding the limit, we are bounding the sequence. And you would bound it from above and below by some sequence that converges to the same number from above and below. So here, how are we going to show that it converges to 0? We'll need to find some sequences that converge to 0 from above and below. And one is very simple. The one at the bottom has to converge to 0, right? Of course, each of these fractions here is bounded below by 0, meaning it's greater than 0. No matter what you take for n, if we agree that a is the term number of the sequence tending to infinity, there will never be a number less than 0 here. It will never even be equal to 0 here, right? Because you won't find an n that makes it equal to 0. But even this bound greater than or equal to 0 is enough for us. So the lower bound is very obvious, right? If someone wanted to be super precise here, they would say it's bounded by the 0 sequence, where every term of that sequence is equal to 0. But the upper bound is not obvious at all, right? We need to come up with a sequence where each term is greater than or equal to the corresponding term of this sequence, and this sequence converges to 0. Well, it's not obvious. What can we figure out? What sequence should we figure out? To figure it out, I'll show you step by step. Let's write down these terms again here in order and expand them a bit more. Let's put a little more effort into expanding rather than just writing down the finished terms, because after simplification, there will be such a term. But even before we get to this simplification, we'll notice something. The first term is 1 factorial divided by 1 to the first power, which is 1 over 1. Okay, great. The second term can be written like this. In the numerator, 2 times 1, in the denominator, 2 to the second power, so you could break it down into 2 fractions. 2 over 2 times 1 over 2. At the top, look, 2 factorial is broken down into 2 fractions. At the bottom, 2 squared is broken down into 2 fractions, 2 times 2. You can write it like that, the second one. The third term. 3 factorial on top and 3 to the third power broken down into 3 fractions. You can write it like this, the third term. The fourth, well, 4 factorial on top, 4 to the fourth power on the bottom. The fifth can be written like this, the sixth can be written like this, the seventh can be written like this, and so on. And actually, every term can be written in this way. Generally every term can be written this way. Let's take a closer look. Firstly, you can notice that each of these, now not terms, but these partial fractions, which are factors of this term, here there is 1, here there are 2, here there are 3, here there are 4, here 5, here there are 6, here 7, here n, some general term. And each of them is less than or equal to 1. Agreed? It must always be smaller. Each of these fractions is less than or equal to 1. The first one at the beginning will be 1, but the following ones will be less than 1. Is that really the case? Could you say that's the case? Well, yes, because look, it's formed such that there's n factorial on top, right? And n factorial will be n, the first one, and multiplied by n diminished already. So in the numerator there will already be a smaller number than that n. So it's obvious that each of these terms is less than or equal to 1. So someone might say, aha, so that means we can bound it by 1, right? This sequence, since each of them is less than or equal to 1, the whole thing is bounded by 1 times 1 times 1 times 1 times 1. Well, you could, right? It's true that it's less than or equal to 1 because each of these terms individually is less than or equal to 1, right? And that's great, but it won't help us at all when it comes to the squeeze theorem. We need to restrict this more strongly, so that it converges to 0 at the top, not to 1, because then we can use the squeeze theorem. Now we know that the limit is somewhere between 0, inclusive, and 1, inclusive. That's not enough. We need to calculate exactly what the limit is. So, this restriction will be too coarse. But let's restrict it even more tightly. The fact that each of these terms is less than or equal to 1 is obvious, but that's still not saying enough. Look, take a close look at them. Some of them are not only less than or equal to 1, but for example here in the second one, less than or equal to 1/2. Here, this second term is less than or equal to 1/2. Here, this third term is less than or equal to 1/2. And in each of these, except for the first one, there will be terms that are not only less than 1, but also less than 1/2. That's also obvious. Here, these two are less than or equal to 1/2. Less than or equal to 1/2, sorry, not just less than 1/2. Here too, right? This first one, this like 2/4, is less than or equal to 1/2, because it is equal to 1/2. Here, there will be these two. Here, there will already be these 3, right? Here, 3 are less than or equal to 1/2. Here too, 3 are less than or equal to 1/2. Agreed. In each of these, we will also find those that are less than or equal to 1/2. In each of these fractions, because they are arranged sequentially up to 1. Here too, there are some less than or equal to 1/2. Generally, in each one. In this first fraction, in each one except the first, right? Because in this first fraction, well, there aren't actually any less than or equal to 1/2 here. But in this second one, there is one less than or equal to 1/2. Here too, there is one less than or equal to 1/2. Here, there are two less than or equal to 1/2. I'm denoting the number of those less than or equal to 1/2 with the letter K. Here too, there are 2. Here, there are already 3. Here, there are already 3. And what will it be in general? Let's think about it now. How many here, if we had, I don't know, 8 factorial over 8 to the 8th? 9 factorial over 9 to the 9th. How many of these fractions here, these factors, will be less than or equal to 1/2? It's clear that well, about half, right? Half, but if there's an even number of them, it will be exactly half. Because it will be exactly the average here between the largest and the smallest. It will be less than or equal to 1/2. But if there's an odd number of them, like here, then not exactly half, because 4/7 is not less than or equal to 1/2. Half, rounded down, so half of 7, which is 3.5, rounded down, that would be 3. If you had 9, right? 9 factorial divided by 9 to the 9th power, then 4 of them would be less than or equal to 1/2. Half of 9, rounded down. It must always be the case in every fraction, because here, the numerators are numbers in sequence from the largest to 1, and the denominator is that largest number. Half of them, rounded down, will be less than or equal to 1/2. How to write that down? Their number divided by 2, so half. Rounding down is this unusual notation. Kind of underlined. It's different in different countries, you know. This notation is like, in English, floor, meaning the floor. Rounding down. If a fraction arises, you round down. Well, of course, the floor, works so that if the number comes out to 3, for example, like here, because 6 divided by 2 is 3, then the result is 3, that rounding. So, the number of factors less than or equal to 1/2 here is half their number, which is n over 2 rounded down. So, this sequence is definitely less than or equal to something like this. If every factor here from the first ones, those greater than 1/2, for example here, look. If you take each of these 5 factors and replace the first 3, this one, and this one, with 1, and these two with 1/2, then the fraction that results will definitely be greater than or equal to this. And similarly here, if you replace the first 4 with 1, so it would be 1 times 1 times 1 times 1, and from there, times 1/2, times 1/2, times 1/2, times 1/2, then the fraction that would result would be greater than or equal to this. That always holds true, right? So, we can bound this entire sequence with a sequence of 1s multiplied by themselves, i.e., to the power of 1/2 rounded up, which is rounding up by the way, meaning we replace the first group of terms, those greater than 1/2, with 1, so it would be 1 times 1 times 1 a corresponding number of times. And immediately replace the second group of terms with 1/2, i.e., 1/2 times 1/2 times 1/2 a corresponding number of times. We would bound this sequence from above with this sequence, because this sequence always has terms that are greater than or equal to this one. And now we just need to show that this sequence here converges to 0, which will be really very simple. Let's move on to the next slide. We have this constraint, we showed on the previous page that it's true. And now let's calculate the limit of the sequence that we showed on the previous slide, which bounds this sequence from above. And how do we calculate this limit? Well, very simply, let's expand it a bit. Here is 1 to the power of, we don't know exactly what, but we know how many times we multiply it. 1 times 1 times 1. How many times do we multiply this 1? Well, that many times, because it's to that power. This is definitely an integer, because it's rounded up, so 1 times 1 times 1. N over 2 rounded up times 1/2. How many times do we multiply it by itself? Up to n divided by 2, rounded down, because it's raised to that power. And notice that 1 times 1 times 1 times 1. No matter how many times we multiply it by itself here, whether it's 10, or 100, or 500, it will always be equal to 1. So it will be something like this, so we have such a limit. And 1/2, if n diverges to infinity, meaning there are more and more and more of these terms, so n is getting bigger and bigger and bigger, so it's 1/2 to the power of infinity, really. So we have 1/2 times 1/2 times 1/2 times 1/2 times 1/2 to infinity. What does this tend to? Undoubtedly to 0. So we have 1 times 0, which is 0, and we've shown that this sequence on top also converges to 0. So, we've shown what we needed to show, and we'll write a nice response to the professor by the squeeze theorem. It needs to be formulated nicely, just as your professor requires at the university. This theorem also has many names, so adapt to the one you use at the university. This limit equals 0. We've shown this because we took a sequence from below that converges to 0, that is, the 0 sequence, and a bounding sequence from above that converges to 0, and we've shown that the limit of this sequence equals 0. And that's it, the problem is done. In this somewhat strange, unusual example. I think, quite difficult. For now, good luck with your studies.